This is our last of 4 videos on reactions. We've looked at 3 other topics regarding reactions, balancing equations. Then we looked at the kind of initial part of stoichiometry, how to work through an equation to solve mathematical problems, how much product do we get from a certain amount of reagent. Then we talked about limiting reagent, and we talked about theoretical yield and actual yield, and how we find percent yield. This last one is just going to look at types, how we categorize reactions. And there's kind of 2 basic ways in which we categorize reactions. We can do that by looking at kind of what is changing. Is it the number of electrons? That's oxidation reduction reactions. Is it a proton being transferred? That would be an acid-base reaction. Or is it just atoms changing partners and who they bond with? That might be a polar reaction. But there are some other ways we categorize reactions where we're not really worried about the details of the actual transfer change, but just kind of what happens to the compounds in general. So if we had like A and a B, there might be a combination of those 2 together. We'd call that either addition reaction or a combination reaction. Also called, I guess, a synthesis reaction. So addition, combination, and synthesis reaction, where we can have 2 become 1. Maybe combination and addition are pretty common. Then there's a type of reaction where we have oxygen involved, reacting with typically carbon to make CO2 and water, or some sort of oxidized form. If it's a complete combustion, we make CO2 and water from hydrocarbons. If it's an incomplete, you can have carbon monoxide and things like that. So the next one is, if this one's a combination, this would be a decomposition where we have things breaking apart. You also may hear of this as an elimination reaction. 2 things form from one thing that was together. Now please know that you can have like a 2 in front of this if you're balancing the equation, and it still means though that if it breaks apart, we still have a decomposition reaction. So don't worry about the coefficients. Look more to what is happening with those, I guess, compounds. If they're coming together, 2 plus 2 gives, let's say we had something like this, 2, 2, and 2, that would still be an addition reaction or a combination. Last 2, this happens really with salt formation. We can have a double displacement where, let's say, A and D get together and B and C get together. It's like a do-si-do, change your partner, ho-si-ho, low ho-down. We're going to have partners change. And this one might be sometimes soluble, but then we'll have something precipitate out of solution. That's called a double displacement reaction, even though these might not actually get together and form a solid that precipitates in solution. Then last, here's a common one. This is a, I guess, single displacement, where we can have, for example, zinc reacting with HCl. We'll need 2 of those to make zinc chloride plus H2. And if you look at what happened there, the zinc is replacing the H in its combination with Cl. So we have the zinc, like A, knocking off B, our H, and making a bond with C and kicking B off to make hydrogen gas. So that's an overview of the type of reactions. We're going to look specifically at 3 types. We're going to look at precipitation reactions, acid-base reactions, and oxidation reduction. So in precipitation reactions, again, we might have, and I have this one down here, we have a double displacement reaction where A is going to get together with D and B is going to get together with C. So we have that. Let's say this one's our B and C. That's solid that's formed. And this one might stay in solution, this combination of A and D. That would be, for this one, we'll say that silver is combining with our chlorine. So I guess we'll have to change that, this solid here. But C and B is representing the sodium nitrate. And typically, group 1 metals, like sodium, like potassium, they don't typically precipitate. They typically stay in solution, and that's what that means, is aqueous. It's not precipitating out. But we still call that a double displacement reaction. 2 elements have switched, 2 partners have switched. A has gone to D, and B has gone to C. We already talked about this example in the last slide, a single replacement reaction. You also call it single displacement. I mentioned that the group 1 metals are often soluble. Now there's just a few things I want my students to know regarding solubility. I want them to know that group 1 metals are often soluble. There's no real exceptions for that. Lithium, sodium, potassium, they tend to be pretty soluble. They don't precipitate with anions. Also that the group, their halogens tend to precipitate, but there's an exception. We'll call it the PMS exception. If fluorine, fluoride, chloride, and bromide are connected to or interacting with the ions lead, mercury, or silver, PMS, P kind of the letter, and PB, lead, mercury, or silver, it tends to precipitate with those halogens. But in general, everything else, it'll be soluble with other types of anions, such as our cations, whether it be lithium or whether it be calcium, strontium, barium. Sulfates, you can kind of see they're not as soluble as our nitrates. This is always soluble, so let's just stay with that. Nitrates are always soluble. Your group 1 metals, lithium, sodium, they're always soluble. And the halogens, unless it's PMS, your lead, mercury, or silver, it's also soluble. There are a lot of things you can memorize, and maybe we should, but I'm going to leave it at just those three. Know that your nitrates are always soluble. Your group 1s, that's your sodium metals, or your salts made using lithium, sodium, and potassium, would be soluble. And in general, salts made using fluoride, chloride, and bromide, other than those PMS, are soluble. I'm going to write the full ionic equation here. If we have aqueous, we often have to have a full ionic equation to illustrate that. So we're going to say 2K plus, and there would be AQs behind it, but for space, I'm just going to say we have this separated into ions, and there would be aqueous symbols behind it. Aqueous, aqueous. Plus our lead, our nitrate is a -1, so this is going to be a 2 plus. And we have 2 nitrates, so we're going to say 2NO3 minus. And that has now taken these salts and shown that they are aqueous. What we've basically done is shown them as separate ions, which is what they would be if they're designated as aqueous. And again, I would have aqueous, 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 aqueous behind it. But just for space, I've kept it, I guess, without those. This is a solid, so that stays the same. But now we notice that we can say 2K plus, because it's aqueous, plus 2 nitrates, because it's aqueous. Now notice there's some things then that are seen on both sides. I'll circle those in red. This is a precipitation reaction. This is the full ionic equation right here, the full ionic equation. But I'm circling what's going to come out when we do net ionic equation. The nitrate, oh, I see that's also on both sides. So really, when we take and cancel these, this is called the full ionic equation, what's in black, I would end up with what's called the net ionic equation. I2, 2 of them, I minus, 2 of those, with the lead, and again we use those aqueous terms, makes lead iodide. Alright, I'll stop there, but that's the idea of full ionic equations and net ionic equations that we derive from that. There's another example down here if you want to check that out. Alright, that's precipitation reactions. Let's move on into other types of reactions. We said there was 2 others that we wanted to look at. Acid-base. I'm not going to spend a lot of time because we'll catch this in another chapter. Acids donate, though. This is the currency, is protons. I know there are some acid-base reactions that are not involving a proton, but just to start, the easiest, I guess, principle we need to remember is that most acids involve donating a proton, an H+, and bases accept. So there's going to be 2 parties in that reaction. Someone donates a proton, and someone accepts. How they work, I guess this is for buffers. We're going to learn a little bit later on. Buffers, in short, are going to keep the pH constant. So we'll see, this is really important. Acid-base chemistry is important in the body because we have a buffering action that keeps the pH constant. We don't want our pH to be jumping up and down in our body. Weak acids react with strong bases. We can have that. Weak bases can react with strong acids, and that's what we'll be looking at later on and quantifying, is that we can have reactions driven by the strong base if it's a weak acid, and a strong acid if it's a weak base. In the end, the initial balance of acidic and basic OHs stays fairly stable if we have a buffer. So we're going to look at buffers later, but just remember, acids donate protons and bases accept protons. Reduction. Now this is something that's often hard for students. You think, well, I'm going to lose something, I'm being reduced. No, reduction is gain. We gain, this is the gain of electrons. Reduction is this guy here accepting the currency, which is the electrons in this case, not protons. It's all about electrons. Electrons flowing from one, compound to another, or one agent to another. Electrons is the key. It's the currency. So if we're gaining electrons, we can say that is being reduced. So this is a reduced compound if it's gaining electrons. Now there's a little mnemonic device, oil rig. Reduction is gain. So if you remember that, you can say, well, then oil rig, oxidation is loss of electrons, because oxidation is loss. So there we go. Those are the basics of oxidation reactions. Somebody has to gain electrons, and that'd be our fella here. He's gaining, so he is reduced. And someone is losing electrons, so he is being oxidized. Now we can determine who's being reduced and oxidized by considering oxidation states. It's just a way to quantify who's got what number of electrons. So a couple principles or rules for this. Oxidation states of an element in its pure form is 0. So this would be things like zinc solid, or hydrogen gas, or oxygen gas. They are going to be considered to have an oxidation state of 0. Oxidation states of representatives in their ionic form, it's their charge. So if we had zinc chloride, ZnCl2, the charge is the oxidation state. That's for salts. When you have a salt, it gets a lot easier. The charge is its oxidation state. So for zinc here, we'd say it has a 2+ charge, but it's also its oxidation state. Please know, and this is the hard thing for students, if we go from a 0 oxidation state for zinc to a +2 or a 2+, it's actually loss, because the currency again is electrons. Electrons have a negative charge. So if I go from 0, you might say down to +2, I'm losing electrons. All right, 2 more. Oxygen is always -2 in a compound, whether it be salt or covalent. There's very few exceptions to that. Peroxide is one of them. And hydrogens with a nonmetal in covalent compounds is always +1. So in front of them, and when mixed with a metal, they can sometimes be -1. But we'll just learn for now that oxygen is always -2 in a compound, and hydrogen's typically a +1. Let's apply this to this reaction below. The oxidation state for sodium pure is 0. The oxidation state for pure Cl2, its elemental form, is 0. When we go to the other side, we know this guy has a charge of +1 and this has a charge of -1, so it's also its oxidation state. Now follow this. The sodium went from 0 to +1, so he lost electrons, because electrons are again negatively charged. But the chlorine, these two, gained electrons. They went from 0 to having a -1 oxidation state, so they gained. I'm going to stop with this slide, and we're going to apply this, but you can actually talk about half reactions to help you understand who was reduced and who was oxidized. So let's look at this one here. Copper solid plus oxygen gas makes copper oxide. We can break it down. Let's look at copper first. Copper goes from an oxidation state of 0 to an oxidation state of 2+. So therefore, he had to lose electrons. He lost. He went from 0 to +2. There were 2 of them that went to +2, so there's 4 electrons that went somewhere else. This would be our half reaction for just copper, and we would say copper is being oxidized. And then last, we can say, looking at the other agent that has to now accept those 4 electrons, O2 is in the 0 oxidation state. It goes to -2 oxidation state because that's its charge in this compound. It had to gain those 4 electrons. So this is the other half reaction, and this guy is being reduced. You guys have hung on for a very long video, but one last thing, this is kind of gets students confused sometimes. if we use the word agent, like oxidizing agent, remember that's the one that's being reduced. It's like someone who's a killing agent. He's not dying, he's going and killing someone else or something. That's a terrible analogy. But the point is if copper is being oxidized, he's giving someone these electrons. So we kind of say he's a reducing agent, the one that's being oxidized. And the one that's gaining electrons, he's not a reducing agent, he's taking electrons from somebody, so he's a oxidizing agent. So this is our oxidizing agent, this O2, and the copper here would be our reducing agent. These are sometimes confusing for students. If it's oxidized, it is the reducing agent. If that O2 is reduced, he is the oxidizing agent. That's it. Bye-bye.